First of all, thank you for giving me the opportunity to present my results about Sculptoris in this our 2020 conference. I'm just quick introduction. I've started my PhD thesis the 1st of October. So I will present to you most of all works that I did during my 3 months internship before starting my PhD, which is about the MATISSE VLTI instrument exploitation and the imagery of evil stars. My PhD director thesis is Pierre Cruzaleb, and my co-director thesis is Florentin Minour. And me, I'm Julien Drevon, and the PhD student, not so much comfortable in front of camera, but that's another story. So the ID card of all Sculptoris. So in quick, some words. So it's an AGB stars, and with a temperature of 2,700 Kelvin roughly, located at a distance of 270 parsec, with the solar masses. Several studies has already been made about the star Sculptoris at different scales. For example, the one of Sculptoris with the Pioneer instrument, and also the famous picture of taken with Halma instruments. What is interesting in the Halma picture at R Scl is we can see the presence of a spiral in the circumstellar envelope of the star. And so this is quite interesting because it's maybe we can think that there is a companion around the star which will induce this kind of shape of the circumstellar envelope. And I've also took AVSO and ASIS data in order to build a Landskarger pyrograph of the star Sculptoris, where we part some different periods. The one roughly 1 year periods and 41 years periods of the star. So now I've talked about Sculptoris. Quick words on the MATISSE instruments. So MATISSE stands for the multi-aperture medium-infrared spectroscopic experiments. So in this work, we only used L-bands and N-band measurements, which has been made with the 80s. In low resolution, and in order to give some numbers for the MATISSE instruments, the limit current flux, meaning for having a signal noise ratio of 10 in good conditions, is 1 Jansky for the L bands and 17 Jansky for the N bands. So MATISSE have observables, and the observables, one of the observable MATISSE is all the visibility. So meaning the fringe contrast. When you have a visibility of 1, you don't resolve the object, and the more you decrease the visibility, the more you resolve the objects. And which make the bridge, the link between the measurements and the physical properties of your object is what we call the Van Titter's dynamic theorem, which link directly the visibilities and the Fourier transform of the source brightness distribution. And so thanks to those visibilities, I tried to build a model with software which is called Dusty. So we put a black body as central source of 2,700 Kelvin. We put a circumstellar envelope mainly composed of amorphous carbon and silicon carbide, and a density law which is driven by radiative driven winds and the solving of hydrodynamic equations. So in this modeling fitting process, we had 2 things. We had this spectral energy distribution and the visibility fitting. For the spectral energy distribution, we have, in fact, 2 things. The photometric points, which has been chosen in order to build a consistent spectral energy distribution, meaning having this photometric data points in the same time of pulsation periods than the pulsation period of the MATISSE observation of Sculptoris, and then the ISO spectra in order to cover all the medium infrared area. But as you may see, since Dusty, in fact, don't handle the molecules, and here you see the molecular features, absorption features in the ISO spectra, we only used the silicon carbide pattern here in order to fit the data in addition to the photometric points. And the visibility on the right, which fit quite well. The model fit quite well with the MATISSE observations. So here is just a sketch on the top right corner about how Dusty consider the model. So central source, central symmetric ports, and central symmetric models with a circumstellar envelope, and a void between the star and the beginning of the formation of dust and the envelope. So MATISSE results confirm with the literature. This is one of the main things that you have to read in these works, that our modeling of the dust is consistent with the different elements and results that we can find in the literature, meaning the dust distribution, the composition of the envelope, the inertial diameter, temperature, limb darkening, etc., etc. So, but since it works for the N band, we have some discrepancies, and meaning modeling improvements that we can do with L bands, because since you know that in L band you have mainly the molecular absorption and molecular informations about the objects, and Dusty don't handle the molecules. So we need to add at some point something which can explain the discrepancies that we see. So for example, here on the bottom left corner, you have the dots, which are the MATISSE measurements, and the line, which are the Dusty model. And you see that for long baseline, for the green dots, you have the central source signature, while in the MATISSE observation, you don't have. So this means that the observations induce something which increase, in fact, the visibility at this spatial frequency. So there is no clear edges of the star, and there is something between the central star and the envelope, which make the visibility increasing for this location there. So we think that there is maybe more or several molecular layers, which is between the circumstellar envelope and the star, which will smooth, in fact, the star edges and increase the visibilities. But in order to, okay, thank you. In order to build, in fact, a model which consider different molecular layers, you need to identify the nature of the molecules. And this is what we are currently doing. We replaced our black body with a stellar atmosphere. We made an identification of each different molecular absorption with the isospectra. And we add on the co-marks, so the stellar atmosphere model, we add some dusts. And you can see that the green curve and the blue curve have still some discrepancies. And those discrepancies is a molecular pattern of around the star Sculptoris. And we identify the transmission function by Gaussian fitting from each particular molecular absorption, and in order to build a more consistent spectral energy distribution, to have a starting point in order to modeling, to start our modeling of molecular structures. And this is my conclusion in perspective slides. So MATISSE result confirmed the literature. We build a model, we're currently building a model with molecule, but we have also image reconstruction with still in process. We have also another closure phase in the closure phase measurements, which means that we, at some point, we need to take into account also asymmetries and several other targets, which are analyses which are coming. Thank you for your attention.
Okay, thank you very much, Julien. Very interesting. There is time only for one question, I believe. Yes. This is from Nasi Anugu. I'm wondering what properties of inner binary causes the spirals result of binary disk interaction in the R Sculptoris.
So, sorry, the question was about the binary?
What properties of inner binary causes the spiral result?
Oh, so we don't know about the binary, but we think that if there is a binary and if this is the responsibility of the spiral arm, we expect, in fact, to have at some point in the closer environment of the star a kind of structure of plume, which is the beginning, in fact, of the spiral pattern, appears in the close environment of the star. and maybe which can lead to some other explanation on the binary or properties. I don't know, because I didn't work on it yet, so I can give you more explanation about